Hello, welcome to this first webinar organized by Lgem. It's great to see that so many people have taken the time to join us today. My name is Jeroen de Vree, I'm a lead sales engineer at Lgem, and I'll be moderating this webinar. And I'm joined today by my colleague, Pieter Oostlander, who's the Chief Science Officer at Lgem. And today we will talk about some of the key aspects of scaling algae production. Feel free to drop any questions you might have in the chat, and we'll try to answer them during the webinar. Scaling algae production typically starts with small-scale experiments, with the aim of obtaining a production process that can be replicated or extrapolated to large scale. Today, Pieter will go through some of the key considerations that we have experienced from a scientific perspective as the main topics to consider when downscaling your process that you want to have at a large scale. And I will share some insights that I've obtained both from internal and external experiences that we've had when scaling algae production processes.
Yeah, so during this webinar, we will touch upon 4 topics to give insights into the approach that we undertake at Lgem to develop microalgae production processes that work at scale. So we typically try to downscale our production system in the lab from what we have at operational scale. So during this, we will touch upon the following 4 considerations. The first one we will look at is the experimental approach that you plan to do in the R&D phase. Then secondly, we will look at the nutrients, how to bring the commercial nutrients to the lab. Thirdly, we will look at the use of light. And then we will look at how to operate the reactor and the advantage of batch versus continuous operation. The first item to consider is the method of performing experiments. And this sounds obvious, but everything in small-scale experiments impacts the results, and we would like to design the experiments in a way that as many items of the experiments can be replicated what happens in the production-scale reactors. And to do so, we don't design from the small reactor, from the small scale up, but we go from what works in the reactor down. And the approach will always focus on what is possible at any scale, and the question, can I repeat this result at the large-scale production system? So when scaling production, we don't look at it from how can we bring the flask into the reactor, but how can we bring the conditions of the reactor to the flask or to the small-scale reactor. So instead of moving from the top left of the slide to the bottom right, we move the other way around. We think about what happens at production scale and how can we bring that to the lab. So that said, we do test relatively few things at flasks or bottles at Lgem, because here we only take a very rough approach just to check, does it work or does it not work? As these systems are controlled to a very low extent. And quite rapidly, we move to more controlled systems, which we typically do in our Lab 5 or 25 systems before we scale up to the envisioned industrial scale process. So if operating at small scale outside of a reactor, what are the main things to consider? So the key factors to keep in mind are that basic systems like flasks or bottles typically have a very relative low degree of control. So there is no complication in terms of sensors or any control loops. So that is complicating the reproducibility and sometimes the accuracy of the results that you will get there. So for example, it's not difficult to change the gas transfer rate in a flask or a bottle, but changing it could have a significant impact on the final results that you will get, and changing the values to match exactly that of what will happen in your big scale reactor, that is very complex. Then also pH control. Without using on-demand CO2 control and a sensor, which would make it a reactor, it's difficult to control it to a high level of accuracy at small scale. Then the mixing regime, it's different at small scale than it is at the reactor, and it also impacts the gas transfer rate. And then reproducibility. So, well, Jeroen, we both have done quite some research back in our PhD days, and we've both used quite some flasks and bottle systems. And I think we both know that the reproducibility is inherently slightly lower if you have no control over most of your variables. And the reproducibility, it's a bit twofold. First, it's repeats between experimental approaches. So if you do a triplicate, how big is your error bar? But then second, which is the most important one, what we're looking at today, is how do we scale what is happening in the small one to the big reactor, and how does it translate? To be able to think about that.
Yes, to add to that, during my PhD, I indeed experienced when doing some bottle experiments that a small difference in the aeration rate or the mixing rate could cause a factor 2 to 4-fold difference in the biomass concentration obtained between duplicates. And yeah, this shows it's a simple, non-controlled system for some basic research or finding directions, but maybe it's not the right tool to develop your process.
Yeah, indeed. And then there are some other aspects, and those are the ones that we will discuss in more detail during this webinar, which is the use of growth media, the application of light, how to think about light, and how is the system operated, which for very small scale systems, it's typically a batch because you just don't have control over these other things. And all of those factors influence the results that you're going to get. So because of those factors, at Lgem, we don't use bottles and flasks that much. But they are an important tool for experimental research. We use them to test if something works, yes or no. Not to quantify, but just to determine, is the media, for example, suitable to go into the reactor? If the answer is yes, then we move to the reactor and go into controlled environments and test all the things that we want. So
you probably mean, does the media allow to support a high enough biomass concentration so it's worthwhile to go to the reactor?
Yeah, indeed. Just checking, does it work? Can we do the basics of what we want to achieve in the reactor? If so, then we can continue. And the optimization of the media and all the growth, it happens in the reactor. So let's look at the bottles, for example. Sometimes we see these used for strain selection or comparing different strains or comparing different conditions. And but what we've seen is that with typically minor changes, such as aeration, that's very difficult to control in an accurate way in the bottles, you can have a large effect on the biomass, as Johan already mentioned shortly. And this means that the reproducibility of the obtained results is limited, but most importantly, it doesn't always scale to the big reactor. We need to really look into the reproducibility of the results.
Yeah, and that's one of the main questions. Do you get what you want at this small scale? What is achievable or commercially you can survive that to achieve that at a large scale? And yeah, we've seen also in our own experiences, both internally and externally, that certain candidate strains were selected from well plates or flasks, and they proved to be the best performer. But when we put them in a different system where the dynamics or the process is different, then sometimes they don't perform as well as they did in a less controlled system. Of course, we do use bottles, as Peter indicated, to do some rough experiments. Does something work or not? Or is it worthwhile to investigate something further? Like recently, we had some experiences with the effect of an ion magnesium on the EPS production of a certain strain.
Yeah, for example, that one, it really helped. We did some quick bottles and flask experiments, and we really saw a big effect already in the bottles. And then changing the media in the reactor made the change that we wanted, but in the bottles and the flask, we were just able to test many more conditions at the same time that you won't be able to do with 10 reactors in a row. But it was a very quick screening, and the result was exactly what we were hoping for.
Yeah, so one of the key take-home message of this part is that, like, sometimes you hope to get an apple, but in reality, you're selecting for maybe a potato crop. And this is the difficulty when downscaling or carrying out lab scale experiments in your process development for something that should happen at the end at a larger scale.
Yeah. So then this brings us to the next consideration, which is the nutrient mix that is used in growing your microalgae. And instead of thinking of it, bringing the lab media to the industrial scale, again, we think about how can we bring whatever we do at industrial scale down to the lab? Because it's really key to understanding how the nutrients will behave also already at your lab scale. So let's look at the differences between lab media or large-scale media. So generally, lab media or cultivation media is developed using pure chemicals that are purchased usually as powders. And they are dissolved in the lab environment, and they make up stocks for the media. This is easy to do at the lab, but it becomes more and more difficult as we move to scale. In the lab conditions, it's easy to control the mixing. The mixing can be very vigorous, so we can easily dissolve all the compounds quickly in a small volume. But as we move to scale, this process is more difficult to replicate. And during the first experimental R&D phase, very few people really consider what kind of nutrient is going to be at the industrial scale, but it's very important to consider. So while using a different form of chemicals can alter the composition of your media. So if you don't use the chemicals from the large scale on the small scale, you might have to redesign everything in your process when you're moving to big scale. So let's look at the larger scale media. So when operating at the larger scale, on industrial scale, we prefer to prioritize liquid media over solids. So we prefer to purchase liquid chemicals rather than solids, because it's just easier to dose and control and pump and mix liquids together at an industrial scale than it is to go and mix all kinds of powders. So one interesting example that we always see is the use of sodium nitrate. In many or almost all laboratory scale media compositions, sodium nitrate is typically used, but it's a chemical that if you move to big scale, it takes a very long time to dissolve. It's an endothermic reaction, so it takes heat, and it requires vigorous mixing. Temperature fluctuations at large scale could influence the solubility of the compound, and it can give you all kinds of problems with filters, pumps, and those kind of things. Therefore, we prefer to operate using nitric acid. Nitric acid is a liquid, it's easier to handle, but it changes the chemistry of your media completely. You don't add any alkalinity with nitrogen consumption, and it adds an acid to the media. So the moment of adding the component to your media is different, and you have to set the pH in a different way. So let's look in a bit more detail at this example. So for example, the lab grade sodium nitrate, you can get it at, and it's relatively expensive, but getting it in bulk, it already becomes quite a bit cheaper, but it never becomes as cheap as the sodium nitrate. So already thinking about what's the impact of the selection of my chemicals on the final cost price of my product, already at lab scale can be very important. Nitric acid is a liquid, it's easy to handle, it's easy to dose, it's relatively stable. It has its problems, but and it's typically readily available on a global scale, as it's also used in cleaning for food factories, for example, or as a horticultural fertilizer. Yeah, next.
Yes, and we have some to add to that. We have some experiences on this specific topic where operators become impatient. They dose huge volumes of sodium nitrate or potassium nitrate, and they throw it in an IBC or the tank where it mixed. At the end, everything sediments in the bottom. The tank clogs up. The pump, the lines around the pump used for mixing can clog up and even potentially break the pump. And that's just, it's difficult to control. It's an operational risk, and we should avoid this. And using nitric acid for that is actually something that we have seen in our own experience that reduces these risks. It comes with some other risks, but it gives you a bit more easier ways of control. Also, the nitric acid is much more stable. Yeah, as a solution under temperature variations.
Yeah. So, Jeroen, I see a question coming in on this topic from Claudio. He says, what about health and safety when handling acids at large scale? Solid salts are way more safe to handle. This is indeed a valid comment, especially when we're looking at acids. The good thing about acids is that there are dosing equipment available on all scales, right? So food industry or even swimming pool equipment, they have dosing pumps that are rated for working with pure acids. The lines can be fully closed. You don't need to handle it. You don't need to touch it. There are safe ways of replacing the IBC in your facility, and there's all safety standards. The other thing, sodium nitrate, we have to mention, in many places, it's highly restricted how to use it because sodium nitrate can be used to create explosives. So that also comes with its own way of handling it. And we have seen that, for us at least, it's easier to make the health and safety work for the acids than it is for the solid sodium nitrate, because you need all kinds of permitting and more difficult paperwork to get sodium nitrate at scale compared to nitric acid. I hope this answers the question. We also must mention, by the way, Jeroen, this nitric acid one or sodium nitrate is just one of the examples. We have to say that it has to do, this is true for many more chemicals in the media composition. So the key message here is think about what the nutrients will be at large scale and use those in the same composition and same method of preparation in your small scale to really make sure that your experiments can be translated to big scale.
Yeah, and don't ignore that it's a factor influencing the production cost of your biomass when doing small-scale experiments, because at the end, you need a commercially viable process.
Yeah, yeah. Okay. So now, if the media is well defined, it's functional at large scale, and it's not your growth limiting factor, then let's turn our attention to light, the driver of photosynthesis and the key component of microalgae production at any scale. But to understand large-scale production correctly, it's key to develop small-scale experiments that resemble light conditions similar to those experienced at large scale. So in this segment, I'd like to explain our approach to scaling light from different scales reactors to large-scale operations. I must say, it's going to be highly simplified, but we have found that this method of thinking about light really works for our experiments and works for scaling what we do from small-scale reactors to the bigger ones. Just to start as an introduction with light, it can be one of the most confusing metrics of photosynthesis. So let's first understand the measurement that we're talking about. Light is usually measured in micromoles per square meter per second, where micromoles is the amount of light, is the amount of light particles, photons, measured on a area, square meters. And we have to keep in mind that these square meters, they have a direction. They are measured in a certain area. So it's either the horizontal floor area or it's the tube surface, but it has a direction in which it's measured. And then there's a unit of time. So micromoles per square meter per second is an amount of light particles, photons, reaching a surface within a given amount of time. When working with artificial light, it's very important to understand that the exact location of the measurement, as a measurement at one spot does not always represent the average of the full reactor area. And this can be confusing when a reactor is sometimes equipped with a light sensor and it's measuring light at only one spot. So for us, what we try to do is the metric of micromoles per square meter per second doesn't really tell that much on what is going on in the reactor, or it completely forgets about reactor geometry. So at Lgem, we like to think about light in a volumetric light supply rate. So the amount of light that we supply to a liter of culture per unit of time. And that can be days, seconds. So here's an example. So let's assume, for example, we have a 1500 micromoles per square meter per second of light sun irradiance that hits a horizontal surface, and that's the left picture that we see. The light is measured on the horizontal floor surface. The direction of the light is vertical. And let's compare that to a reactor where the tubes are stacked and the light is measured in the horizontal direction and the area is vertical. So to do that, we need to take the amount of sunlight that we have. Then we need to take into account the reactor geometry. So how many tubes do we have? How many floor meters do they use? What's the volume of the tubes? Those kind of things. And then we can convert the light that we have from the sun to an amount of light that we can have per unit of culture. And doing it that way, we can convert a peak light intensity from the sun, for example, 1500 micromoles per square meter per second, to a volumetric light supply rate.
Yeah, that's a very interesting approach, Peter. We're not seeing a lot of comments yet in the chat, but I do expect that this will be a large topic of discussion. I remember that when we were designing our Lab 5 reactor, we got requests of fitting it out with over 2000 micromoles per square meter per second. This was technically a bit challenging for this lab scale system, but even when we started to consider how this would work at an industrial scale, we were like, hey, this can't really work, or is complicated to arrange at a very large scale. And it, of course, the higher light intensities, when light is the only limiting substrate, will give you the highest results to report or data. But can we achieve this at a large scale?
Oh, yeah, sorry. So let's look at the numbers, for example. So, Let's look at this example calculation here. So if we take the amount of light, 1500 from the sun, and we convert that to a volumetric light supply rate, given our Entel system, which is our biggest production system available at the moment, that converts to around 20 micromoles per liter of culture per second. This all has to do with the reactor geometry. This then equates to around 440 micromoles per square meter per second on the vertical surface measured in the horizontal direction on this same reactor, on average over the full reactor. Now, if we start doing experiments and we want to keep the volumetric light supply rate, so this 20 micromoles per liter of culture per second, equal between all the experiments, and then we apply the reactor geometry of all the other Lgem systems, so we have the pilot scale systems, which have a slightly different geometry, or the lab scale systems, which have an even smaller tube diameter, we can see that to reach the same amount of light per volume equal to this 1500 micromoles of light in the sun, we would need only 150 micromoles per square meter per second on the reactor tube surface area. So here you can see that putting 2000 on that surface would be an extreme amount of light for the volume that is available in the reactor. So these numbers really show you that when we're dealing with light, we really need to think about what does the reactor geometry do, what are the volumes, what are the intensities that we have, and how do we scale an experiment that we want to do at big scale down to the smaller scale. So for us, if we run an experiment that we want to replicate what's going to happen in the biggest production system in our Entels, we set the light is on the lab 5, so the smallest reactor, at 150 micromoles per square meter per second.
And I see we have a good question from Jian Wei, and we are indeed referring to the culture volume in the reactor.
Yes. So this is a good point in the question segment. This is culture volume, so liquid. And as most of our audience might be aware, the Lgem tube system operates as a two-phase flow. So there's also an air bubble in the system, but we're referring to the liquid volume that's in the tubes. Hope that helps.
And Peter, you're giving a lot of numbers and details. Aren't we going a bit too much in detail right now on this specific topic?
Well, yeah, I might end up in a bit much detail. And we haven't even talked about the spectrum of light, the colors, the electricity requirements, the heat that gets off your lights, or even sunlight and daily fluctuations. So let's not go into all of that right now. Could be interesting for a next webinar in the future.
And please let us know if you find this interesting in the chat.
Yeah. So let's move away from light for now. And let's talk a bit about our fourth consideration, which is how to operate the reactor. When operating a reactor, there are always multiple options, right? So, and while most of these decisions at scale are typically based on the DSP equipment that you have available or how you want to run your operations, it's good to already apply the same methods at lab scale. Right, so let's look at some of examples of the fermentation industry because they have nice pictures available. So we've borrowed those. But when operating in batch, which is the top picture, we have to start with a very low biomass concentration and a very high concentration of all the nutrients because we want to supply all the nutrients for the growth already from the start of the experiment. And then towards the end of the experiment, the nutrients go down, the biomass goes up. Nutrient concentration is never stable, the biomass concentration is never stable, and as a result, the light supply is also never really stable. Then there's the option of moving to semi-continuous, which is the bottom picture that we see here. And from the graph, we can see the fluctuation scale of individual harvesting moments. For example, this would be a reactor where we would harvest once per week a large volume. If we increase the amounts of time that we harvest, so maybe we do twice a week a harvest, but still there are going to be fluctuations. You have to supply the nutrients for the next few days of growth. Whereas if we want to operate in a continuous mode, we would like to keep as many of the parameters, so light or nutrients or biomass concentration, we would like to keep as much of those as constant as possible so we can really investigate what the effect of changing one of those parameters is.
On the performance of the culture, product of interest content, I would assume.
Yes, on many factors, right? Because as you say, on the content of interest, let's assume that we try to achieve a certain pigment in the biomass. It really depends on what moment in your batch are you harvesting, and what the concentration is of the certain component that you want. And if you are able to contain all the parameters steady, that means that the pigment of interest is also going to be steady. So for us, continuous operation is a preferred method of performing our research. So continuous operation aims at keeping the conditions for growth stable. And for photobioreactor operations, there are a few versions based on the method of control. Those are turbidostat, luminostat, or chemostat. Those are the main ones I want to touch upon right now. In turbidostat, typically, we try to aim to keep the biomass concentration stable in the system. At luminostat, you typically try to aim to keep the light, depends on how you define it, either per volume or per biomass, usually it's per biomass, stable in the system. But those require sensors and specific control loops. Whereas if you go chemostat is a method of supplying a fixed flow of fresh water or fresh nutrients to the culture and a fixed flow of harvest out of the culture. This makes it that the only control you need is a steady running pump, and they'll be available on industrial scale. So that's not going to be the challenge. You don't need complex control loops, but you can keep everything steady. So a stable dilution rate in the reactor, there's a constant free media going in, harvest going out, and the biomass will adapt to the situation and reach a steady state. And in this steady state, the nutrients are stable, the biomass is stable, and also the biomass composition, as we just touched upon, will remain stable. Well, we have to note that continuous operation, of course, it doesn't work for all applications. For example, if you want to do xanthin, where you need a green phase and then a red phase, then you specifically want to have the characteristics of a batch process where you want to run out of a certain nutrient or introduce a certain amount of stress to your culture to achieve what you want. So there are specific examples where this doesn't apply. Then to give it some context, there's a small subset of a data set that we've made using chemostat. So here we show that we've grown multiple different species with a dilution rate varying between 20% to 50% per day. So up to half the culture volume is replaced every day and harvested every day under continuous conditions. So that means 24 hours per day of light. And we can see that the impact of the dilution rate results in different biomass productivities with an optimum around maybe 30%, 40%, something in that range, depending on the species that is used. And then if we were to change another parameter, so let's say the chemostat is stable and the dilution rate is stable, and we change one of the components in the media, the effect of that individual change has a direct effect of what the biomass productivity will be. So we can really measure the effect of individual changes to the culture media, to the light, to the whatever, maybe temperature, whatever parameter you want to change. So this really gives us a powerful tool to test at lab scale with the smaller reactors, how we really want to operate the big reactor in the future.
Yes, and yeah, we have also seen some really nice results from this. Peter showed some data before. This was only on 4 strains that we selected. We're now up to 10 strains, and we really use this research methodology to define the operational window for the operation at the end for the large-scale systems within our facility. And we've seen good positive results. We've seen that we can get large uptime, like 90 days is nothing uncommon in our results. I also saw before a comment actually from mice about the control of contamination. This is not really a topic in this webinar, but we've seen that by adjusting the dilution rate, we could use this as a control strategy to control the level of contamination. Of course, we have other design characteristics that we use when we are engineering and designing our reactors. I'm happy to chat about that. Maybe that's also a topic for another webinar. Yeah, and at the end, so at this lab scale, when we're developing the production process, we are working on a 24/7 light condition, so 24 hours a day light. And this gives us a lot of, it's easy to operate. We don't have a day-night sign. We don't have variation with this day-night sign. And we can just really focus on defining the operational window for operation. And at the end, I personally believe that large-scale factories will be operating 24/7. Maybe not everywhere in the world, like sunlight-driven scenarios, but maybe that has a different time horizon than indoor production today.
Yeah, indeed. Yes, Jeroen. So I think with this, we're already reaching our the end of the time of this webinar. So I'd like to summarize some small take-home messages for our audience. So if your small-scale experiment is aiming at achieving results that can really be replicated at large scale, we need to make sure that the experiment that we're doing at small scale is designed well. And there are many aspects to think about. And today we only touched upon 4. So let's recap those for a little bit, right? Think about the light. Is the light in the lab really relevant at the large scale that we want to produce at? We've seen that with conversion factors of calculating how the light per volume works, there can really be a difference in what you need to apply in different scales. Think about nutrients. Are you using a nutrient recipe that can actually be directly implemented at scale, or does it need changes for easier handling or processing, or maybe even production cost reduction? Think about the stability. Are you really looking at the effect of the parameter measured, or are many other things impacting your results? And in the end, it all comes down to reproducibility, and that's twofold. Can I reproduce the experiment in lab multiple times after each other? But also, can I reproduce the result from the small scale really at the lab scale? The large scale, sorry. And with that, a small overview of the Lgem approach on how we try to scale our production processes from small to large. We do start with bottles and flasks, but the only thing we test is, do we have good confidence that this media will support a high biomass concentration in the reactor, and will it work? If the result is positive, move to the smallest reactor we have as soon as possible. Here we can go into chemostat operation, stable operation, and we can start testing with strain selections, or we can start testing media designs by tweaking the components one by one. We can test different dilution rates. We can test the effect of light on the culture, and start really configuring the final production process that we want to do at large scale, while always thinking about, will whatever we do here really scale to the big scale? And then, if it all works and we found a sweet spot, let's move to scale. So let's validate what we've tested in the lab or in the pilot really in the big reactor systems. And that's really what we're trying to achieve when we scale our processes.
So with this, we are at the end of this first webinar from Lgem side. I really enjoyed doing this with you, even though it's a bit exciting. I see that we have quite some interaction in the chat, which is very nice. We'll try to answer some of the questions still in a bit. And if you have any questions, don't hesitate to reach out to us. If you want to know more about how we think we can grow any LG at any scale, please reach out. And some things to discuss, like I saw a comment on the circulation pumps, and we, for example, and the shear stress. So we specifically choose very low shear pumps that actually the most fragile algae species could actually survive. However, our systems also work very well with the liquid pump completely off.
Yeah, well, let's not forget the two-phase flow. The Lgem system runs typically with no pump at all. So this really reduces the shear stress. It is also a very difficult factor to really mimic at small scale and really know what your big pump is going to be. But by eliminating the need for a liquid pump in the reactor altogether, it reduces another risk of scaling. So that really helps.
Yeah, and I saw also a question earlier from Emil about the volumetric flow and oh, no, that was not it, but it was about the minimum biomass concentration for inoculation. We also have some guidelines internally on that. Maybe you can elaborate a bit on that.
Yeah, so typically when we scale, right, we want to take a small reactor to a bigger reactor. We always assume that we can do a 10 or maybe 20-fold dilution series. So if we have a reactor that is 20 liters, that is our Lab 25 system, we use that one, grow it to a high biomass concentration of maybe 5, 6, 7 grams per liter. Then we use that volume to inoculate the pilot 925, which holds around 600-700 liters of culture. So there is almost a 20-fold dilution rate between those. And then we try to achieve a biomass concentration of at least 0.2, but preferably 0.3 grams per liter to start a good reactor. So to start a nice reactor, that's around where you want to be.
Yeah, and then we basically achieve a 98-99% success rate after inoculation when we carry out experiments, right?
Yeah, indeed.
I see another question from Peter, actually, about the volumetric light measurement and how do you account for the fact that light penetration is low? And I think also that is connected to our two-phase operation of our systems, the waves traveling through our reactors.
Yeah, so by having enough movement in the reactor and having enough turbulence in the tubes, the algae cells that will be on the outside will quickly move to the inside and the light will be distributed over the volume that way. Another way to think about it, if we run chemostat experiments, the culture will find the balance of how fast it can grow given the conditions of light, dilution rate, nutrients, those kind of things. So you will find the productivity that is the sweet spot for the culture with that light conditions. But Jeroen, I think some of those questions are really great, but I don't think we have time to go into all the detail for all of them. So we will have to finalize it here. If you have any further questions or would like to have some discussions with us directly, feel free to reach out, contact Lgem and see what we can do for you to help scale your process for any algae to any scale.
Yes, and last comment, you can download and review the recorded webinar after it's finished.
And we'd like to thank you for your attendance and hopefully see you at the next webinar.